trying to get into AI, especially generative AI, large language models, all that,
Yeah.
it can really feel like, well, like hitting a wall of jargon, right?
Oh, absolutely. It's easy to feel overwhelmed, like you need a PhD just to follow along sometimes.
Exactly. Which is why we wanted to do this deep dive. We found this great source, an article by Victor Leung, Essential Concepts in Generative AI Continuous Improvement.
Mm-hmm.
And the cool thing is, he wrote it because he was working through these terms himself, as a solution architect. Wanted to make it clearer.
Yeah, he saw that need, right, to break down these sort of fundamental ideas for folks who aren't maybe building the models, but definitely need to understand them.
So that's our goal today. We're going to unpack these key concepts using his article as our guide. Just pull out the essentials so you can really get a better sense of how this stuff actually works.
Right, aiming for clarity, not just a list of terms.
Right.
Enough insight so you feel more comfortable when these topics come up.
Exactly, feeling informed. Okay, so let's jump in. Where do we start? I guess, how does an AI even begin to understand text, the input part?
Well, it doesn't read like we do, word by word. The source talks about something called subword tokenization.
Subword tokenization. Okay.
Yeah, the problem it tackles is, well, the sheer number of words out there. Rare words, new words, slang.
How does it handle that? Breaking words down.
Exactly. Into smaller, common pieces. So instead of unbelievable being one unknown thing, it might see believable.
Okay.
And the source really highlights the benefit. The model learns these pieces so it can then understand, or at least make a good guess at new or rare words just by combining those familiar parts.
Right, like word Lego bricks. Much more adaptable than just whole words. Okay, what about weird formatting, like accented letters or symbols that might look the same to us?
Good question. That's tackled by Unicode normalization. Sometimes the same letter, like A, can be represented differently in the computer's code. Normalization basically standardizes all that. Make sure A is always represented the same way. The source points out this stops the model getting confused, treating the same thing as different, just because of, tiny encoding differences.
Okay, makes sense. Clean up the input first, standardize everything. Now, these models, they often have limits, right, on how much text they can chew on at once.
They do, yeah. Memory limits, processing limits.
So how do they handle, say, a really long article or a whole book?
That's where chunking comes in. According to the source, it's pretty much what it sounds like.
Breaking it up.
Yep. Breaking the long document into smaller, manageable chunks. The benefit highlighted is, well, it's much easier for the AI to find and process the relevant bits of information it needs from a huge text instead of trying to, swallow the whole thing whole.
Okay, so just recapping this input stage. We've got breaking words into bits, tokenization, making sure characters are consistent, normalization, and chopping up long texts, chunking. It's all about prepping the text.
Exactly, setting the stage for understanding.
Great. So the text is prepped. How does the AI actually start to figure out the meaning, the relationships between words? Because, order matters, context matters.
Right, this is where we get into the model's processing engine. One big challenge, especially for these modern transformer models, that process words kind of in parallel.
They lose the sequence.
They can, yeah. The parallel processing means the natural order isn't inherent. So they need something extra to tell them where each word was in the sentence.
And the source calls that?
Positional encoding.
Okay.
Basically, it adds a little bit of information to each word's representation it's embedding that signals its original position.
Ah, okay.
And the source stresses how crucial this is. Without it, like you said, dog bites man and man bites dog would look the same to the model. The meaning depends on that order.
Right. Completely different situations. So positional encoding gives it the sequence back. Now it knows the words and their order. How does it connect related ideas, especially if they're far apart, like pronoun references or complex dependencies?
Yeah, that's the magic of attention. Specifically, the source mentions multi-head attention, which is key in these transformer models.
Multi-head. Sounds complex.
It kind of is, but the core idea, as the source explains it, is that it lets the model look at different parts of the input sentence at the same time. It weighs the importance of all other words when processing a single word.
So it's not just looking left and right, but kind of everywhere at once, with multiple focus points.
That's a good way to put it. And the source actually gives a little peek under the hood, mentioning Q, query, K, key, and V, value matrices.
Q, K, V.
Okay, think of it like this. The query Q is the current word the model's focused on. It uses this query to check against all the keys, K, which represent all the other words, to find the most relevant ones. Then it pulls the information, the meaning from the values V of those relevant words.
Okay, so Q is what I need info about, K is what info is available elsewhere, and V is the actual info, and the matrices help manage that search.
Exactly. It's how the model dynamically figures out which other words are most important for understanding the current word, no matter where they are in the text. It's fundamental to how they grasp long-range context.
That's really fascinating. Okay, so through all this, especially in deep networks with tons of layers, things could get messy numerically, right? Values getting too big or too small.
Absolutely. That can destabilize the whole learning process.
How do they manage that?
That's where layer normalization comes in. The source describes its function as basically keeping things balanced. It adjusts the values within each layer to stay within a stable range, preventing them from exploding or vanishing.
Right. Keeps the calculations on an even keel during training. Okay, so let's review again. AI reads text using tokenization, normalization, chunking. It understands order via positional encoding, relationships via multi-head attention, and keeps numbers stable with layer normalization. Phew.
That covers getting the info in and processed, yeah.
Now, how do they actually learn and become more efficient at it?
Okay, now we're talking training. One basic component the source mentions are activation functions. Things like ReLU and sigmoid.
Activation functions. What do they do?
They're crucial for letting the model learn complex patterns. They introduce non-linearity. Think of them as decision points or gates within the network's neurons.
Gates.
Yeah, they control whether and how strongly a signal passes through a neuron. The source contrasts ReLU, which is computationally efficient and common in deep networks, with sigmoid, which is often used for outputs that need to be probabilities because it squishes values between 0 and 1.
Got it. Different gates for different jobs. Now, the source also flagged a big challenge in training deep models.
Ah, yes, the vanishing gradient problem. It's a classic issue.
Sounds bad. What is it?
So during training, the model learns by adjusting its internal parameters based on error signals, called gradients. In very deep networks, these signals have to travel backwards through many layers.
Okay.
The problem is they can get smaller and smaller with each step back. Vanishingly small.
Like a whisper fading out.
Exactly. Which means the layers near the beginning of the network barely get updated. They stop learning effectively. The source notes that ReLU actually helps mitigate this compared to some older activation functions.
Interesting. So a problem and part of the solution connection there. Okay. Shifting to efficiency. These models are massive. How do they make them practical? Smaller? Faster?
One key technique is quantization. The source describes it as essentially shrinking the model.
Shrinking? How?
By using less precise numbers, smaller numerical formats to represent the model's parameters, its weights and activations. Fewer bits per number means less memory, less computation, often leading to faster performance, with maybe only a small hit to accuracy.
Using rougher estimates to save space and time. Clever. And memory itself is a big deal, right? Training these things must take tons of RAM or VRAM.
Huge amounts. That's where memory pooling comes in,
Yeah.
as mentioned in the source. It's about efficient memory management. Instead of constantly allocating and freeing memory blocks, which is slow, pooling techniques allow the system to reuse chunks of memory quickly during both training and inference when the model is running. It's critical for fitting large models onto the available hardware.
Makes sense. Reuse, reduce. Okay, what about learning when you don't have a zillion examples? Can AI learn from just a few?
Yes, and that's super important. It's called few-shot learning. The source highlights this ability for models to generalize to perform a new task pretty well after seeing only a handful of examples, maybe just 1 or 2 shots.
Instead of needing thousands, wow.
Exactly. It makes AI much more adaptable without needing massive, task-specific data sets every time.
And related to that, what about reusing knowledge? If a model learns one thing, can that help it learn something else faster?
Definitely. That's transfer learning. The force explains it as leveraging the knowledge, the features, the patterns, learned by a model trained on one task, usually a large general task.
Like understanding language generally.
Right. And then you transfer that knowledge to a new related task. It saves a huge amount of training time and data because the model isn't starting from scratch.
So learn cats, then learn dogs faster using the cat knowledge.
Pretty much, yeah. And one more technique the source mentions for improving how models reason is chain of thought prompting.
Ah, I've heard of this, making the AI show its work.
That's the gist. The source draws an analogy to how we humans often solve problems step by step. You prompt the model not just for the answer, but to outline its reasoning process first.
And that helps.
Often leads to more accurate and reliable results, especially for complex problems, because it forces a more structured thought process, so to speak.
Feels like a step towards more understandable AI. Okay, huge amount on learning and efficiency there. But how do we know if any of this is actually working well? How do we measure performance?
Evaluation is key, absolutely. The source mentions a few methods to make sure your testing is fair, especially if you have different categories in your data.
Like testing medical diagnosis on different patient groups.
Exactly. You'd use something like stratified k-fold cross-validation. The source explains its function is to ensure that when you split your data for testing, each split or fold gets a proportional representation of all the important categories. Avoids accidentally testing only on easy cases, for instance.
Smart. Ensures a balanced test. What if you have two models, like version 1 and version 2, and want to know if version 2 is really better statistically?
For that, the source points to the paired t-test. It's a standard statistical method used specifically to compare two related groups, like the performance of two models, on the exact same set of test data, to see if the difference you observe is likely real or just due to chance.
So, proper scientific comparison. Okay, what about specific tasks like translation? How do you score that automatically?
A very common metric mentioned is BLEU scores. BLE stands for Bilingual Evaluation Understudy. The source explains it works by comparing the machine's translation to one or more high-quality human translations. It looks for overlapping sequences of words, pairs, triplets, quadruplets, n-grams. More overlap generally means a better translation.
Checking how many phrases match the human version makes sense. And for summaries, if an AI summarizes an article?
For that, the source mentions ROGE scores. ROGE stands for Recall-Oriented Understudy for Gesting Evaluation.
Another acronym.
Yeah. ROGE also compares the AI-generated summary against human-written reference summaries. But it focuses more on matching important words or sequences, looking at things like recall. Did the summary capture the key points from the references?
Got it. BLEU for translation closeness, ROGE for summary content overlap, different tools for different jobs.
Exactly. Objective measures to track progress.
Okay, nearly there. Let's wrap up with a few specific, powerful techniques and applications highlighted in the source. Something about efficiency again. Batching.
Yeah, dynamic batching. So normally, AI might process data in fixed chunks, fixed batch sizes. Dynamic batching, as the source describes it, is more flexible. The system can adjust the size of the batches on the fly, based on maybe the length of the inputs or current system load. The goal is better hardware utilization, getting more work done faster.
Adapting to the flow. Smart. And speaking of hardware, there was that really long phrase about GPUs.
Yes. GPU-accelerated columnar data processing with zero copy memory access. That's a mouthful.
What's the core idea there?
Okay, so GPUs are great for parallel tasks. Columnar data is like spreadsheets data in columns. This technique uses GPUs to process that kind of data really fast. The zero copy part, highlighted in the source, is key. It avoids slowly copying data back and forth between the main computer memory, CPU, and the GPU's memory. Less copying means much faster processing for large data sets.
Cutting out the middleman transfer time. Got it. Specialized speed boost.
Crucial for big data analytics.
Okay, shifting to generation. How do models create those incredibly realistic images or text? The source mentioned diffusion models.
Right, diffusion models are really powerful for generation. The source breaks it down into two stages.
Okay.
First, a forward diffusion process. You start with real data, like an image, and you deliberately add noise, step by step, until it's basically just static.
You destroy the image. Why?
Because then you train the model on the reverse process. The reverse diffusion learns how to take that static, that noise, and carefully remove it, step by step, to reconstruct or generate a clean, coherent image or piece of text.
Wow. So it learns creation by mastering noise removal. That's quite a concept.
It's complex, but incredibly effective for generating high-fidelity outputs.
Okay. And back to making AI more factual. We hear this acronym a lot now, RE.
Retrieval Augmented Generation. Yes, the source emphasizes this one. It's a major technique for tackling AI, making stuff up hallucinations.
How does it work?
The core idea from the source. Before the AI generates an answer, it first retrieves relevant information from a trusted knowledge base, like a specific set of documents or a database.
It looks things up first.
Exactly. It then uses that retrieved information as context to generate its response. So the answer is grounded in actual data, not just the patterns it learned during training.
That seems huge for reliability, like giving the AI research
This
skills.
is a really important development, yeah. moving beyond just its internal knowledge.
And finally, the source touched on computer vision outside of text.
Yeah, just briefly. It mentioned image transformation techniques used during training. Things like randomly flipping images horizontally, rotating them slightly, zooming in or out.
Why do that?
The source explains it helps the model learn that an object is still the same object, even if its appearance changes slightly. A cat is still a cat if it's facing left or right, or if it's bigger or smaller in the frame. It makes the model much better at recognizing things in the messy real world.
Builds robustness, makes the AI less easily fooled by variation.
Exactly. Better generalization.
Okay, wow. We have really covered a lot of ground just from this one source. We went from the very basics of how AI ingests text.
Yeah. Tokenization, normalization, chunking.
How it processes meaning with positional encoding and that crucial multi-head attention.
Yeah, right. And keeping stable with layer norm.
Then into how it learns activation functions, tackling vanishing gradients, efficiency tricks like quantization and pooling, learning from few examples, transfer learning, chain of thought.
All the training strategies.
Then how we measure success with things like stratified validation, t-tests, BLEU, and FRU scores.
Evaluation metrics, yeah.
And finally, these powerful specific techniques like dynamic batching, the GPU optimization, diffusion models for creation, RG for factuality, and image transformations.
And the key point the source makes is that these aren't just abstract terms. They are like the active ingredients being constantly tweaked and improved to build the AI tools we're seeing emerge.
Which really brings it back to you listening. Having even just a basic grasp of these concepts, tokenization, attention, RG, helps you understand what's going on when you use AI or hear about the latest breakthroughs.
Yeah, it gives you a better sense of the capabilities, maybe some of the hype, and also the limitations. What these systems can and can't do well, and why.
Totally. It helps you feel more informed. So here's something to think about based on all this. We've seen how these concepts are the building blocks, and they're constantly being refined, made faster, smarter, more reliable.
Continuous improvement, like the article title says.
Right. So thinking about that constant evolution, what new possibilities or maybe even unexpected changes do you think might emerge as these fundamental concepts keep getting better and combined in new ways? What happens when all these pieces get just a little bit smarter together?